Lecture 8C didn't do as many problems as I think you really need to understand the concept check. So I'm going to record just a couple of extra ones here to give you a little bit more background. So let's start off with an example where we're looking for a probability of obtaining a sample mean that is similar to the mean that we actually get from a sample, or one larger, so I'm thinking I'm going to be to the right on a curve, for a population in which I have a mu of 4, and then this one's gone ahead and given me an S of 2, and that's fine. It's not really realistic because chances are I'm not going to know population data, but we can deal with that as we get into the tests of inference. So let's go ahead and just set this up so that we understand what's going to happen. I'm going to start off with normal distribution, or it could be not normal. Honestly, it doesn't really matter, but I'm going to go ahead and draw it normal for right now. Because remember, the central limit set theorem says that you can sample from a non-normal distribution, and the distribution of those sample means will then become normal. So I'm going to go ahead and just draw it normal so that we can compare and contrast these guys. Now, I know that when I take a sample, and in this case n is 3, that I shrink the standard deviation because we're removing some variance when we take sample means. That is a horrible looking normal curve. Oh well. So my mean will theoretically stay the same, but now my standard deviation units should look closer. And to figure out how much closer, what we need to do is we need to calculate S hat and then use S hat as an estimate for sigma, and then calculate sigma sub x bar from that value and the square root of n. So just going through the motions here, I can already tell what my answer is going to be, but I'm going to go through the motions just because you won't always be quite that obvious. So my x values are 4, 6, and 8, and my x minus x bar values, well, the mean's 6. I mean, I could add it up, I'd get 18. 18 divided by 3 is 6. Or I could just eyeball it, because I see that 4 and 8 are equal on either side of this middle number 6, so my mean is going to be 6. So x minus x bar, 4 minus 6 is negative 2, 6 minus 6 is 0, and 8 minus 6 is positive 2. Now I need to square those deviations. Gotten pretty good at this. Negative 2 quantity squared is 4, 0 squared is 0, and 2 quantity squared is 4. So my sum of squared deviations is 8. So to calculate S hat, I'm going to take that sum of squared deviations, 8, divided by n minus 1. So that's n minus 1, n is 3, so divided by 2. The square root of 8 over 2 is the same as the square root of 4, which equals 2. And you'll notice it conveniently matches what the problem actually stated. We'll do one here in a little bit where it doesn't. But I actually think all of the ones in your concept check match. Pretty sure. Alright, so I've got my S hat, but I'm not done with it. I need to calculate sigma sub x bar, because remember, it's got to shrink, and it hasn't shrunk because it's still 2 if I just use S hat. So to find sigma sub x bar, we're going to use S hat as our estimate of the population standard deviation, and then we need to divide by the square root of n. So I take S hat of 2, divide by the square root of 3, type that in my calculator, and it spits out 1.1547 and a couple of zeros. That makes sense because my standard deviation was 2, now it's 1 in a little bit, so it did shrink. And if I now set up the number line for my distribution there, 4 plus 1.1547 is 5.1547, plus another 1.1547 gives me 6.3094. Now go the other way. 4 minus that sigma sub x bar gives me 2.8453, and minus it again, I get 1.6906. All right. Now, the question asks, obtaining a sample mean or one larger as the one from the actual sample we're using. And that had a mean of 6. So, I'm going to change colors here. A 6 would be somewhere right around here-ish. And I want or larger, so I'm looking at the tail region, which makes me think, oh yeah, I need column C when I use the table. I can also kind of estimate my value for the z-score, which is what I'm going to need to find the area under the normal curve for column C. And so I can see that I'm between a z of +1 and +2 and likely closer to the +2 one. So I wouldn't be surprised if I got a z of like +1.7-ish. So let's calculate it. So the score of interest is 6 minus the mean, which is 4, all over the standard deviation of this guy, which remember is sigma sub x bar, which was at 1.1547. So I've got 2 divided by 1.1547, and sure enough, my predictions are pretty good. 1.732 something something something. I only worry about this many digits because I know the table only reads to the two digits. So I just need to check to see if I need to round. I don't. So I go to my table, I'm looking for column C, and I see the probability of obtaining a sample mean of 6 from the original population is pretty rare, less than a 5% chance. So 0.0418 is the answer to the question, what is the probability of attaining a sample mean or one larger from a population? Let's do another one. Okay, same game. The only thing that I really changed on this one is I went for or smaller. So now we're looking to the left. It's still going to be a tail region, so we're still going to use column C, but the tail region will give us the or less part. Okay, so -1, 0, 1. And remember, what we do here is we remember that the original population spread, which is defined by these guys, will shrink as a result of graphing the sampling mean distribution. So if I draw it for an n equals 3, now it's going to be more narrow. Okay, I just double checked this, and I did actually intend to add a 4th score to this one, just to switch it up a little bit, and that 4th score is going to be 2. So now my n is 4. Okay, so otherwise same game. The difference here is that we're going to actually have to use our calculated S hat because it won't match. I wanted to throw this in just in case they threw us a curveball in the SPATS test bank. So we have 4 values of x, -1, 0, +1, and +2. The mean of this, you might be getting good at seeing this, but it's 0.5. Of course, I could just add that up as well. The 1 and the -1 cancel. The 2 and the 0 add to 2. 2 divided by 4 is a half, or 0.5. So my deviations, x minus x bar, -1 minus 0.5 makes it more negative, -1.5. 0 minus 0.5 is -0.5. 1 minus 0.5 is +0.5. And then, of course, 2 minus 1.5 is, or 0.5 is 1.5. And at this point in time, you should say to yourself, oh yeah, that is correct, because the sum of these guys is 0, which is a true property of a mean. Okay, so square these puppies. 15 times 15 is 225, so that means this is going to be 2.25. 5 times 5 is 25, so this one's going to be 0.25. So this is the next one. And the last one It's the same. Might as well use the easy numbers. And I see here I actually have a whole. If I add up all those quarters, 2 plus 2 is 4, plus 1 more gives me a sum of squared deviations of 5. So to find s hat, I need to take the square root of that sum of squared deviations divided by n minus 1. N being 4, 4 minus 1 is 3. So I get an s hat. In my calculator, I'm typing square root of 5 divided by 3 using parentheses around the 5/3 so that the square root encompasses both the top and the bottom of that. And I get a value of s hat equals 1.29099 something something something. Now, your brain might have just went, wait, it didn't shrink. Well, it's not supposed to yet. We haven't done this sigma sub x bar. We've only done s hat. So we have another step before we can set up our second distribution. We need to do sigma sub x bar, which we're going to use s hat to estimate the population standard deviation divided by the square root of n, n being 4. So I need to take sigma sub x bar equals 1.29099 divided by square root of 4 is 2. And I get a sigma sub x bar for this bottom distribution, which is still centered around 1, central limit theorem, right, with a sigma sub x bar of 0.64597. Okay, I know I'm looking for that mean that is 0.5 or smaller. If I take 1 minus my sigma sub x bar, I can see that I'm going to be within 1 standard deviation of the mean, so I get 0.3545, meaning, I'll change colors again when I get to this stage, 0.5 will be somewhere around here-ish, and I want lower. So again, column C. My z-score should be point something. That's how I do all these estimates and know which part of the table to put up first. So point something negative. And let's see, to find that, I'm going to take my score of interest, which is 0.5, because that's the thing we're comparing. The mean is 1, all over sigma sub x bar, 0.64597. So it's going to be negative 0.5 divided by the sigma sub x bar, and I get a negative 0.7746. I do not need to round. Remember, don't look 2 away. Only look 1 away from the digit that you're trying to determine rounding for. I don't round here, so I'm going to look up 0.77 on the table. There it is. And I would like the value corresponding to the area under the curve to the left, which is C, because that's the tail, and I get 0.2206. So there is a probability of about 1 in 5, basically, because that would be 20%. It's 22%. 0.2206. That if I really took a sample of 4 scores from this original distribution, that they would have a mean on their own of 0.5 or less. Last example. In this one, I do know the population standard deviation. That's what makes this one unique from the others. I know that the population standard deviation, sigma, is 2, and it matches a mean of 4. And this is actually really important because in this example, they don't give us a sample that actually have numbers with them. It's just more of a theoretical what-if kind of question. So I understand that the original population spread will shrink if I plot sample means. And in this case, I'm plotting sample means for n equals 4. So since I know the x bar of, the mu of the population is 4 and the sigma is 2, one of the assumptions of the central limit theorem is that the mu stays the same. but the sigma will shrink. Sigma will shrink to sigma sub x bar, which is sigma over the root of n. N being 4, I'm going to end up with 2 over 2, which is 1. So it shrunk this guy by half, so it should be twice as skinny. Alright, and then, oh look, how nice. Because with this, I can see that a score of 5, which is our score of interest, our score of 5 lies right on a standard deviation line. And being right on a standard deviation line means that I don't even have to do a z calculation, because I know, since it's one standard deviation above the mean, that is a z of 1.00. And again, I want the tail, and that gives me the 16% I expected, or rounded, it was 16%, but probability is 0.1587, that from a population with these characteristics of mu and sigma, that I could pull a sample of size 4 that had a mean of 5 or greater, and that probability would only be 0.16-ish. Okay, I hope that helps you do a little bit more of the 8C work. And if you have other questions, please remember I am available for virtual conferences, or we can meet at my Starbucks.